talking about gases because gases are something that we've all had some common experience working with in our lives. We have gas in our tires. We live in a sea of gaseous elements. And so gases are something that's relatively common experience to us. So gases are kind of fun to talk about. All right, properties of gases. These are things you probably already have observed on your own. They have an indefinite shape. You have a container of gas. You open up the container of gas. It's going to move out into the air. They have very low densities. Gas densities are recorded in grams per liter rather than grams per milliliter. And we use grams per liter because you need a larger volume of gas in order for it to have a mass. Gases can compress. The whole hydraulics industry is based on that idea. So gases can compress, which leads us to pressure changes. Gases expand, of course, and then they mix completely with other gases and make complete homogeneous solutions when they are in gaseous state. All right, so indefinite shape, low densities, expand and contract, and they make homogeneous solutions. Gas pressure has to do with molecules bouncing around. So we have to kind of change our paradigm and how we're thinking about things. And we have to think about things now not in solid state, not in liquid state where you have aqueous solutions and they're rolling around. Now they have complete random movement. And we're going to talk about physical properties of gases. And those physical properties we're going to measure with one of the few things we can actually measure about a contained gas is its pressure. So what causes pressure in gases? What causes pressure? So before we can even talk about gases, we kind of have to talk about pressure in gases. How about this? What are the units that we use to measure pressure? If you say, okay, what is atmospheric pressure measured in? PSI. What does PSI stand for?
Pounds per square inch.
Pounds per inch squared. All right. What other units of pressure do we use commonly? Well, there's atmospheres, right? Mm-hmm. There is millimeters of mercury. Does anybody know where millimeters of mercury comes from?
Thermometer.
It's not a thermometer, it's barometer. Pretty close. It measures atmospheric pressure. We have torrs, named after Vermicelli Torr, Italian chemist who did a lot of work in gases. We have, what was the other one?
G's, right.
That's physics, yeah. They use a lot of that kind of stuff in physics. So these are mostly the units that we're going to be working with, and you're going to have to transfer things. Now, PSI I like because this tells us what pressure is. It's some unit of force over some surface area. That's what pressure is force over some surface area. And the force for gases is the molecules colliding. They collide with each other, they collide with the container, the walls of the container. And if we had a closed container, like in the picture that you just saw, and we had a pressure gauge, we could say, all right, what kind of things could we change about this container that might change the pressure? Well, before we can think about that, let's talk about the units of pressure. Standard atmospheric pressure at sea level is 1 atm. Okay, so if we were in San Diego, it would be at 1 atm. Here in Chandler, or a little bit above sea level, so our atmospheric pressure is a little bit less. And that's kind of interesting. If you're on the planet here you are standing on the planet, the gas molecules where we are much closer together, right? Because there's a lot of air on top of us. If you go on top of a mountain, they say the air is thinner. Does that mean the molecules get skinnier? No, that just means that there's more space in between them, right? And so there's less atmospheric pressure. So here at sea level, or in San Diego, it's about 1 atm. You go up to the Rocky Mountains, it's something like 0.8 or 0.9. It's much less. 1 atm is equal to, I believe, 14.7 psi. And we do have to change units in pressure, just like we have to change units in temperature when we're talking about gas laws. 14.7 psi is also equal to 760 millimeters of mercury. So those are all conversion factors that you're going to have to be able to use. And generally, we're going to want to do most of our calculations in ATM. So let's do just a little quick practice calculation. If I said I had a pressure of 800 millimeters of mercury, I want to know how many ATMs that is. I have to use an equivalency to go from millimeters of mercury to ATMs. So I start with 800 millimeters of mercury, And I want to use this equivalency between millimeters of mercury and ATM. So I'm going to take my units and substance, mm, Hg, and put it on the bottom so they cancel. And then I'm going to put the units that I want on the top. Now I have to look at the numerical values for the equivalencies. It's 760 to 1 are the numbers that we use there. So now in my calculator, I'm going to punch in 800. 1.05, and that's because I'm going to divide 800 by 760, 1.05 ATMs. All right, so you may have to make conversions between units of pressure, but these are the three big units that we use. Oh, and this is also equal, all of these are also equal to 760 torr. So torr and millimeters of mercury are about the same. All right, so pressure is caused by molecules hitting each other or molecules hitting the side of the container like in the illustration there. Now we need to think about the types of things that might increase or decrease the pressure and talk about whose law is each one of these discussing. I'm not going to go out onto these web links because we know what happens when I do that with my media here, but I'm going to encourage you guys to because it actually gives some nice animations and you can vary some of the conditions in the animation and see how they're affected. Let's think about just our own volume versus pressure. All right, now they have a different kind of container. Now they have a container where you can increase or decrease the size of the container. So let's go back and talk about that issue, volume versus pressure. This is what we call Boyle's law. You need to know whose law deals with which variables for the exam as well as for the quiz that you're going to take next week. So Boyle's law has to do with volume versus pressure. All right, so say we have a container of gas, and I'm going to put my pressure gauge out to the side here. That tells me what the pressure is. And keep in mind, pressure increases when molecules start hitting each other more frequently. Pressure decreases when the molecules hit each other less frequently. All right, so now I have a piston in my container. And I can make the container's size decrease or increase by moving the piston up or down. So I'm going to draw some gas molecules in there so that we get the idea of what's going on here. All right. So when I take the pressure, or actually, you know what? Let's vary our volume. If we decrease the volume, okay, so I'm going to make this go down, right? So I'm going to decrease the size of the container. No longer is it going to have that space. Now these molecules are going to have to exist in a much smaller area. What's going to happen to the volume, or excuse me, what's going to happen to the pressure when I decrease the volume? Pressure is going to go up. And we call this an inversely proportional relationship. And that means not only does one go up but the other goes down, but it goes up by the same proportion. So if I decrease the volume to half, so if I decrease the volume to 1/2, then the pressure would go up by how much? By 2 times as much, right? If I decrease the volume to 1/3 its original volume, how much would the pressure go up? By 3 times as much. Okay, that's what we mean by inversely proportional. As one goes down, the other goes up in direct proportion. All right, so that's Boyle's law. Make sure that you remember the laws and who's responsible for inventing each of these laws. All right, temperature versus pressure. I always thought Boyle and Charles should have changed their laws because it would be easier to remember that temperature had something to do with boils, right? So there's my mnemonic device for remembering the difference between Boyle's and Charles. Is Boyle and Charles should have changed laws so that Charles could have the one that didn't deal with temperature and Boyle could have had the one that dealt with temperature. All right, so temperature versus pressure. So let's think about that in the relationship of the variables. All right, so now I have a container where the size does not change. Okay, I'm going to keep the size the same, so volume remains constant. And here, in this one, Boyle's law, temperature is constant, right? Because if we decrease the size of the container and increase the temperature, that would be unfair. We want to keep the things that might influence our variables the same. All right, so temperature versus pressure. So now I take my container of gas, and I've got some pressure measurement, and I'm going to put it under a Bunsen burner. I'm going to make those molecules do what? When I start heating them up, what are those molecules going to do? They're going to move around a whole lot faster every time I heat them up. So what's that going to do to the pressure? If the temperature goes up, then that means the pressure is going to go up. All right? If I take the temperature and I decrease it, what's going to happen to the pressure? Pressure is going to decrease. We call this a directly proportional relationship. So it's exactly opposite of volume and pressure. Temperature and pressure are directly related. So one goes up, the other goes up, the other one goes down, the other goes down by the same proportion. Same way. And the last one, molecules versus pressure. This one actually has a law associated with it. Do you guys have any idea whose law this is? Molecules versus pressure? Who was the guy that talked about how many molecules is in a mole? Avogadro. This is Avogadro's law. I'm surprised that the person who made the PowerPoint here forgot to put that, right? Number of pieces versus pressure, which is Avogadro's law. All right. Avogadro's law. Well, that makes sense, right? Now we have a container whose size does not change. It's got some gas molecules in it, but now over here, I have a big gas tank, right? There's my gas tank. And I have a stopcock here. And I'm going to open the stopcock, and I'm going to let more gas go in. So if I increase the number of pieces, what's that going to do to the pressure? Increase. Pressure's going to go up. So we call that what kind of relationship? Directly. See, this all makes a whole lot of sense, right? It all makes a whole lot of sense. We're going to talk about the combined gas law in just a minute. You know what, before we go there, let's talk about a couple other quick characteristics of gases. Say, for example, now most gases, whenever they're in a container, they're all going to act the same. And that's because if you have a whole bunch of different gases in a container, say something like hydrogen. And what's the formula for hydrogen? H2. All right, so there's an H2 molecule. We might have an He molecule. We might have an N2, which is going to be significantly larger. We might have a CO2, carbon dioxide, which would be really a lot bigger, right? We might have, what other kind of gases could we have? We might have some oxygen, right? So those would be a little bit larger. All right, if they're all at the same temperature, say they're all at 23 degrees Celsius, they all have the same kinetic energy. But what did Einstein say kinetic energy was equal to, his famous equation? Equals mc squared. Well, it's 1/2 the mass times the square of the velocity. He was talking specifically about kinetic energy here. So 1/2 the mass times the square of the velocity gives you an idea of kinetic energy. Well, if we say kinetic energy in this case is measured by the temperature, are they all traveling at the same, well, let me ask you this question even before we ask you that. Do they all have the same mass, all those molecules? No, they don't. Who's going to be the lightest?
Hydrogen.
Hydrogen and helium are going to be pretty darn light. Who's going to be the heaviest? Carbon dioxide and nitrogen would probably be pretty beefy and heavy, right? All right, so the masses change. Well, if the kinetic energy is always the same, 23 degrees Celsius, the masses change. What has to happen to the velocity of those so that that number stays the same? Velocity has to, if this one's going up, that has to go down. And it has to go down by a square value rather than a half a value, which is actually much more significant, right? I would rather have, if my salary was X, right? Would I rather have 2X or X squared?
X squared.
I'd way rather have X squared if my salary was X, right, rather than 2X. So this has to go down significantly. So if they're all at 23 degrees, who is traveling the slowest? The beefy ones, right? Because they have the most mass. Who's traveling the fastest? The itty bitty ones. All right, but if they're all at 23 degrees, they all have the same amount of kinetic energy. All right, now we're going to use some of these in the combined gas laws. Now where we have the calculation. So now's where you're going to need your calculators, combined gas laws. And let's summarize. If you can remember these two things, PV equals nRT, Pivnert, my second favorite chemistry algorithm ever. I was talking to a physicist, Jenny Pauls. Does anybody have Jenny Pauls? Okay, I love Jenny. We are super good friends. We were talking about gas laws one time, and we were talking about how to solve a problem. And she says, oh, they gather this and this and this. And she goes, and then what do we do? And I go, oh, Pivnert. And she goes, what? I go, Pivnert. She goes, what are you talking about? PV equals nRT. Oh, ha, ha. We laughed for 10 minutes about Pivnert. So only chemists who get the inside joke, right, would get Pivnert. All right, P is what variable? Pressure. And in gas law calculations, we need our pressure in ATMs. So that's why I gave you the ability to change units from one to another. V must be equal to what? Volume. And what are the system's international units that we would use for volume? Liters. All right. T, I know you all know what T is. Temperature. Now in gases, we have to do our temperature calculations in Kelvin. Does anybody have any idea why we have to do our calculations? There's no negative numbers. In Celsius and Fahrenheit, there's always negative numbers. So when you multiply anything by a negative number, what do you get? A negative. So you can't have a negative pressure or a negative volume unless we live like in a black hole or something, right? So we can't have to have it in Kelvin temperatures. N. What is N? Anybody remember what N is? We've used it a couple times for this. Number of moles. N in statistics is usually a number of pieces, so I think that's why the chemists decided to use N rather than like M or something like that for moles. So number of moles, right? 6.02. And R is what we call the gas law constant. And a constant means it's a number that doesn't change, and it's 0.0821 liters times ATM per mole N times Kelvin. All right, that is called the ideal gas law, and we use it to do combined gas law problems. And if you can remember this formula and the fact that if the variables are on, so variables are on the same side versus opposite sides. All right, let's think about that. Variables on the same side. We just talked about these variables, pressure and volume. How are pressure and volume related? Inversely or directly?
Inversely.
Inversely. So if they're on the same side, they are inversely related. If they're on opposite sides, say, for example, pressure and temperature. If I increase the temperature, what's going to happen to the pressure? It's going to go. So they are directly proportional. Related, I mean proportional. I should probably use proportional. That's a better science term rather than related, so proportional. All right, so if you can remember this formula and those two ideas, you can do any of the gas law calculations in this entire chapter. Now, Corwin is going to tell you a whole bunch of different ways, and that's fine. If you like his ways, go for it and do his ways, and that's okay. As long as you get the right answer, I don't care. But I'm going to show you how to do these with just some logical ratio conversions. All right. I like to do these with a story, so let's use this. We're going to say we got a little kid here, and little kid's got a balloon, right? And invariably, unless you tie that balloon around the little kid's wrist, invariably, what are they going to do? They're going to let it go. I can't tell you how many times my own sons did that. Once we were in Costco, and it went all the way up in the rafters, and my son was like, well, Mom, just go get it. I didn't bring my springy shoes, son. All right, so if we let it go, here we are, and it's a sunny day in Arizona, right? So we've got an atmospheric pressure of, it's probably 740 millimeters of mercury. And the temperature is 23 degrees Celsius at ground level. And little kid lets that balloon go. And it goes up into the atmosphere, and the temperature doesn't change, right? Because it didn't go very far, but the pressure went down. The pressure went down to 700 millimeters of mercury. And my original volume of my balloon was 1.2 liters. And I want to know, what's the new volume? Because it's going to change. All right? So my advice is always to set up a grid. And I do this with all gas law problems. I have initial and final values. You can just make like a tic-tac-toe. And then you isolate the variables in question to organize things, right? This is physics, once again, taught me this. Draw pictures with stuff. So in this case, we're dealing with pressure and volume, because remember the temperature stayed the same. So it's 23 degrees up here. It didn't change. So the variables that we're worried about are the pressure and the volume that are going to be affecting each other. So pressure and volume, I want to keep track of them so that when I'm setting up my problems, I can do that. So I have initial and final values for both pressure and volume. So my initial pressure, before my young man here let the balloon go, 740 millimeters of mercury. And my initial volume was 1.2 liters. It went up to, my final pressure now is 700 millimeters of mercury. And we need to figure out what the new volume is. See how I'm relating the variables here and organizing them? Now we've got to do something first before we can do the problem. Remember, that has to do with the units that we should work in. What's wrong with my units? I think these units are okay, but I should change this to what? ATM. Let's change them to ATM. 740 millimeters of mercury and 700 millimeters of mercury. 760 to 1 ATM. So somebody with a calculator, do these for me. Thank you. What's the next one? 700 divided by 760 is what?
0.921.
921. Okay. Oh, that's ATMs. All right, so now I'm going to put my variables in correct form in my organizational chart here. All right. Now here's where the pedal meets the metal. Got to set up the problem. I'm going to show you two ways to set it up. You pick whichever way you like. I'll show you my way, and then I'll show you Corwin's way. All right. Well, you start with the thing that you know is changing. In this case, the thing that's changing, the thing that I have the unknown for that I have to solve, is my volume. So that's the number I want to start with. So I'm going to start with my 1.2 liters as my volume. All right. Now that I've got my volume, I got to set up a conversion factor. And the conversion factor has to come from the variable that's changing. In this case, pressure is the thing that's changing, is going to affect the volume of the balloon. So what's happening to pressure? It's going from 0.973 to 0.921. All right, so pressure's going down. So I always make a little notation to myself that that variable is going down, and I put it in the column just to remind myself. All right, pressure's going down. So now I look back at my rules, and I say, all right, I know the rules are that pressure and volume are on the same side of the equation. If they're on the same side of the equation, they are inversely related, right? You follow me so far? All right, if they're inversely related and pressure's going down, what's going to happen to volume? It's going to go up. So you just make a little arrow that says that number has to get larger, bigger, right? That's the key. All right. Now it's downhill from here. Once you figured that out, you say, okay, I want that number to get bigger using a ratio that I create out of these two numbers. So if I need to create a ratio out of those two numbers to make that number get bigger, I'm going to put the big one on the top and the small one on the bottom. Okay, I'm going to go through that logic again, just so that everybody can see what I did. Let you write that down. All right, so let's go through our logic train again. We said pressure's decreasing. First I had to change it to the units. Say pressure's going down. Pressure and volume are on the same side. That means they're inversely related. If one goes up, the other goes down. Since pressure was going down, volume's got to go up. That number has to get larger. Since that number has to get larger, when I set up a conversion factor out of my variables that are changing, I'm going to put the bigger one on top. So now with my calculator, how I'm going to input this is I'm going to put in 1.2 times, open parentheses, 0.973 divided by 0.921, close parentheses, enter. 27?
Not 6, but
27, okay. And what are my units here? Liters. I actually probably would round that to 1.3 just because we only have 2 sig figs there. Right? Okay, now we're having fun. Let's do another one. Now we got that same balloon, but now when it starts out, what did our old atmospheric pressure say? We're going to be up in the Colorado Rocky Mountains when we let this one go. So the initial atmospheric pressure is going to be, we'll say it's 0.76 ATMs. And it goes very high up in the air, and it's going to go down really low to 0.65 ATMs. The temperature when you let it go is pretty chilly. We'll say it's 15 degrees Celsius. And it gets even chillier when it goes up in the mountains, bless you. We'll say it gets down to 5 degrees Celsius. All right, so now our balloon is going to start out, it's a big balloon. It's like a weather balloon. We'll say it's like a 5.5 liter weather balloon. All right, so let's set up our variables here. Now I have more than just two with initial and final conditions. Actually, no, I have two still. That's right. So now I have pressure, and I have temperature. Oh, I do have three. And volume, right? So I got three things that I have to keep track of. All right, my initial ground level. And this is why I like to draw pictures. My initial values for pressure are 0.76 ATMs. My initial temperature is 15 degrees Celsius. My initial volume is 5.5 liters. Once the balloon goes aloft, it goes down to 0.65 ATMs, 5 degrees Celsius, and we got to figure out what our new volume is going to be, right? All right, we got to change, our pressure units are good, but what units do we have to change in order to make it copacetic here?
Temperature.
We've got to change our temperature value. So Celsius plus 273 is Kelvin. So somebody add 273 to 15. So 273, 278, 288. Thank you. All right. So now same thing. You're going to start with your variable that's changing, the 5.5 liters. Oh, I didn't show you the Corwin way to do this, did I? I'll show you that on Monday. All right. Now we've got two variables that are affecting the volume, right? Temperature is changing and pressure is changing. You have to deal with each one of those independently. So let's do that. All right, let's look at pressure. What's happening to pressure? Pressure's going down. And using my rules, since pressure and volume are on the same side, they're inversely related. If pressure's going down, what's that going to do to volume? It's going to go up. So I want to make that number get bigger, right? Using this ratio. So if I'm going to make a ratio out of those numbers and I want it to get bigger, which one do I put on top? The 0.76 and the 0.65. All right, now I make a little notation to myself. I have dealt with pressure. I'm going to put it aside. I'm all done dealing with pressure. Now I'm going to deal with temperature independent. What's happening to temperature? Temperature's going down. So let's look at our rules. Volume and temperature on opposite sides of the equation. So that means they're directly related rather than inversely. So if temperature's going down, what's that going to do to the volume? That makes sense, right? Stuff gets colder, it's going to decrease. And so now we want this number to get smaller using this ratio. So if I want that number to get smaller using this ratio, which one would I put on top? There it is. Let me show you the Corwin way. It's actually using algorithms. Probably spelled algorithm right, but that's close enough. All right. Corwin says that if you got piv nerd on one side, actually, this is called the combined gas law, that you put them all together. And in this problem, we're dealing with only pressure, temperature, and volume. So we only need pressure, temperature, and volume. We don't need to deal with number of moles because the amount of gas in the balloon didn't change. So these are initial and final conditions. You can still use your grid that tells you how to organize things and use it in this way. So now you just put initial pressure, in this case, 0.76 ATMs. You put the initial volume, in this case, 5.5 liters. You put the initial temperature, in this case, 288 Kelvin. And you set it equal to our final pressure, in this case, 0.65 ATMs, our final volume, we don't know, right? And our final temperature, which was 278 Kelvin. Now, you should be able to, using some algebra skills, solve that particular expression, right?
Yeah.
The problem happens when we get the x down here in the denominator, and people solve and they don't realize it's 1 over x. So in that case, it's always better to use my ratio conversions, but if you like the algorithm method better, have at it. All right, there you go.
That's for next semester. That's when I get into biostatistics. That's the one.
This is Chem 130.
I have a question.
Hang on a second, let me get all this closed.